Hi everyone, I'm Aiganym, a 12th grade student. I have PhysicsHL among my TP subjects, hence I'll be teaching you physics TP topics. Our first topic is measurement and uncertainties. So the very first subunit is measurements in physics. As you might already know, there are two types of units in physics, fundamental and derived. First of all, what is a unit? A unit is a standard measure of a quantity. For example, mass equals to 100 kilograms. Here, mass is a quantity, 100 is a magnitude, and kilogram is a unit. The International System of Units, also known as SI, is the fundamental set of units that are used in physics. These units include meter, kilogram, second, ampere, Kelvin, mole, and candela. Derived SI units are a combination of two or more SI-based units. Any physical quantity other than the 7 fundamental quantities has units that are a combination of two or more SI-based units. For example, Hertz, a unit of frequency, is a second in the power of -1. Newton is a kilogram multiplied by meter multiplied by second in the power of -2. In physics, we often get really low numbers, which is not convenient to write. In such situations, scientific notations help us to write those low numbers in a more efficient and easier way. For example, speed of light. Instead of writing the whole approximate value of 300,000 kilometers per second, we can use scientific notation and write it shortly as 3.0 multiplied by 10 in the power of 8 meters per second. You don't have to remember all the prefixes because all of them are included in the data booklet. Here are some questions for you to practice using the scientific notation. 3,600 can be written as 3.6 multiplied by 10 in the power of 3, and the second number can be written as 2 multiplied by 10 in the power of -8. Significant figures is a fundamental topic, as often in the final exams you might lose some points due to an incorrect number of significant figures in the answer. Significant figures are the digits of a number that are meaningful in terms of accuracy. The number of decimal places is the number of digits to the right of a decimal point. There are several rules which will help you to understand how to count significant figures. All non-zero digits are significant, zeros between non-zero digits are significant, zeros at the end of an integer are not significant, zeros before the first non-zero digit are not significant, zeros at the end of a number with a decimal point are significant. Let's practice. Here are the numbers, and you should identify the correct amount of significant digits and decimal places. 0.0050 has two significant figures because all non-zero digits are significant and zeros at the end of a number with a decimal point are significant, and there are 4 decimal places. 2000 has one significant figure because it's an integer number and zeros at the end of an integer are not significant. There are 0 decimal places. 102 has 3 significant figures because zeros between non-zero digits are significant. There are also 0 decimal places. Now let's move on to mathematical operations and see how to write the final answer in the examinations. When adding and subtracting, the number of decimal places in the final answer must be equal to the least number of decimal places in the numbers added or subtracted. For example, 1.22 plus 10.4632 equals 11.68. As you can see, 2 is the least number of decimal places. Therefore, the final answer also has 2 decimal places. When multiplying and dividing, the number of significant figures in the final answer must be equal to the least number of significant figures in the numbers involved and in the calculation. For example, 3.04 multiplied by 2 equals 6. As the least number of significant figures in this calculation is 1, the final answer also has only one significant figure. Order of magnitude is the power of 10 that the number is closest to. For example, mass of a rock is 86 kilograms. For this value, the order of magnitude is 10 in the power of 2 kilograms. Orders of magnitude are often used to make estimates and approximate comparisons in scientific notation. It helps to represent numbers that are comparatively larger or smaller than other numbers. An estimation is a rough calculation or an educated guess to produce an approximation to the true value. I got few questions regarding estimations in my formative and summative assessments, so even though estimations are not that hard, you may come across such questions in the final exam. We have finished with the first subunit, and now we are moving on to the next one, which is uncertainties and errors. Firstly, let's talk about errors. There are two types of errors, random and systematic. Systematic errors bias measurements always in the same direction, that is, measurements are always larger or always smaller than the true value. However, random errors affect measurements in an arbitrary way. Measurements are spread around the true value, some are larger, some are smaller. There are also two other concepts that are important in making conclusions to the experiment: accuracy and precision. A measurement is accurate if systematic errors are small. Accurate measurements are close to the accepted value for that quantity. A measurement is precise if random errors are small. Repeated measurements of a quantity are precise if all the values are similar to each other. So here's an example of errors. First diagram has no errors, therefore obtained results are accurate and precise. Second diagram shows random errors because results are close to the true value, hence the results are accurate. They are not precise because the obtained results are not similar to each other. Third diagram depicts systematic error because all obtained results are larger than the true value. Since the results are similar to each other, they are precise but not accurate. There are three ways of presenting uncertainty in the answer: absolute, fractional, and percentage uncertainty. So what is meant by uncertainty? Uncertainty expresses the range of values within which a measurement is likely to lie. The best estimate for any quantity, for example the quantity y in our case, is the average of n measurements of y. For small samples, the absolute uncertainty in the average of y is given approximately by the formula delta y equals maximum value of y minus minimum value of y divided by 2. Then the final answer will look like measured value of y equals best estimate of y plus minus delta y. There are some guidelines for quoting uncertainties as best estimate of y plus minus absolute uncertainty. Absolute uncertainty should have only one significant figure. If the first digit in the absolute uncertainty is 1, two significant figures may be used in some cases. Best estimate must have the same number of decimal places as absolute uncertainty, and both best estimate and absolute uncertainty should be expressed in the same units. Now let's talk about fractional and percentage uncertainties. Fractional uncertainty is the ratio of the absolute uncertainty to the best estimate. Percentage uncertainty, on the other hand, is obtained by multiplying the fractional uncertainty by 100%. Propagation of uncertainties is a must-to-know topic, especially when doing IA. Firstly, we'll talk about addition and subtraction. When we add or subtract quantities, we always add their absolute uncertainties. And if a quantity is multiplied by a constant, its absolute uncertainty is also multiplied by that constant. When we multiply or divide quantities, we always add their fractional or percentage uncertainties. And if a quantity is multiplied by a constant, its fractional and percentage uncertainties are not affected. Here are some other examples of propagation of uncertainties regarding powers, inverse value, roots, and inverse roots. It's crucial to calculate the uncertainties of devices that you use in experiments. Each measuring instrument has an intrinsic uncertainty. This intrinsic uncertainty of the measuring instrument is the smallest possible uncertainty in any reading on that instrument. The absolute uncertainty in reading an analog measuring instrument is half the smallest deviation on the scale. For example, the uncertainty of a ruler. Smallest deviation of a common ruler is 1 mm. Hence, the absolute uncertainty is 0.5 millimeters. When we, for example, measure the time using a stopwatch, the absolute uncertainty in reading of such digital measuring instrument is the smallest deviation on the scale. This means plus minus 1 on the last decimal place. Smallest deviation in this particular case is 0.01 seconds, and the absolute uncertainty is also 0.01 second. When the uncertainty is larger than the intrinsic uncertainty of the instruments, we need to estimate the uncertainty. Also, when taking a reading, your line of sight should always be perpendicular to the scale you are using. Otherwise, parallax error will occur. While doing your IA, you will have to present a graph with error bars. Error bars are vertical and horizontal lines which indicate the absolute uncertainty of each data point on a graph. In this certain graph, the uncertainty of the point for y coordinate is 0.5 plus minus 0.2, and for x coordinate it's 0.6 plus minus 0.1. You should also include uncertainty of the gradient and intercepts of your graph in internal assessment. Firstly, when you draw your graph, of course your data will not be perfect, and the line also will not pass all the data points. Therefore, you will draw a line of best fit. Line of best fit is a line through a scatter plot of data points that best expresses the relationship between those points. Line of best fit does not need to start from origin. It may show a systematic error if it passes far from origin on a linear relationship. It should extend beyond the range of data points and should have even distribution of points on either side of the line along the full length. It should touch at least one error bar from each data point, but it doesn't need to touch all data points and doesn't even need to touch any point. Also, outliers might be ignored for the line of best fit. When calculating the gradient of your graph, you should choose 2 points that are far from each other and use the formula delta y divided by delta x. The second graph depicts best fit line in blue color, line of greatest gradient in green, and line of smallest gradient in red. Here are some formulas to calculate uncertainty in gradient and uncertainty in y-intercept. The last subunit of this topic is vectors and scalars. As you might already be familiar with these terms, scalar quantities have magnitude only and vector quantities have both magnitude and direction. Scalars include distance, speed, mass, time, energy, volume, density, pressure, electric charge, and temperature. While vectors include displacement, velocity, acceleration, force, and momentum. A vector quantity is represented by a vector or a line with an arrow. The direction of the vector is the direction of the quantity it represents. The length of the line is equal to the magnitude of the vector to a chosen scale. To distinguish a direction from its opposite direction, we give the vectors opposite signs, positive and negative. You are free to choose which direction you want to be positive, but we usually follow this convention. Let's talk about mathematical operations with vectors. First, multiplication and division of vectors by scalars. You can also use these rules with division, as dividing by scalar n is the same as multiplying by 1 divided by n. When a vector is multiplied by a scalar, the product is always a vector. The magnitude of the vector is multiplied by that scalar. The direction is unchanged if the scalar is positive, and if the scalar is negative, the product is in the opposite direction. When adding vectors graphically, all vectors must be drawn to scale. Draw the vectors so they start at a common point O. Complete the parallelogram with dashed lines. The resultant vector starts at O and is the diagonal of the parallelogram. Alternatively, draw the tail of one vector starting at the head of the other vector. The resultant vector goes from tail to head. If there are vectors with arrows pointing in the same sense, forming closed polygons like in this picture, it adds up to 0. Subtraction of vectors might be confusing, but it's kind of the same as addition because, for example, b minus a equals b plus negative a. Positive a and negative a have the same magnitude but opposite directions. If both vectors start at the same point, the vector b minus a starts at the head of a and ends at the head of b. Resolving a vector means to find its components along any axis. For example, to find Vx, you should use the formula Vx equals V cosine theta. To find Vy, you should use the formula Vy equals V sine theta. And to find the resultant vector v, you should use the formula tangent theta equals vy divided by vx. When adding and subtracting vectors in one dimension, you just need to add magnitudes with signs according to directions. If vectors are at right angles to each other, use Pythagoras theorem. When adding or subtracting vectors in general case, you should resolve each vector in two directions at right angles. Add all components in each direction, and now you have the components of the resultant vector. You should now combine both components using Pythagoras theorem and use trigonometric functions to find the direction of the resultant vector. It's also recommended that you sketch a vector diagram in all cases so that you will avoid making mistakes. Here you can see a data booklet reference with all the necessary formulas for this unit. That's it for today's lesson. I hope everything was helpful and easy to understand. Good luck with all your exams. Goodbye.